watching this recording. And okay, we just started. Hello, everyone who's watching the recording. Sorry, I'm a bit new to this. This is all a bit of a novelty, but welcome to the ELSOC crash course for 2134. I'll just turn off my video now and let's have a look at this paper. So we start out, I might just draw attention to sort of our classic, these are our formulae that we always get given. So it's essentially our Fourier transform pair, the Fourier series, which we might use, and then also a way to derive each of these coefficients an and bm. There's also the complex Fourier series and determining the coefficients, which we might use for some derivations, but in practice we normally stick with an and bm. Okay, so question 1 starts with impedances with an angle of 5 0 degrees. And the frequency that we're looking at, this is an important thing to note as well, is 5 kilohertz. So we're looking for the voltage across each impedance Z1 and Z2. So let's say V1 first. So we're given that I is equal to 5 0 degrees, F is equal to 5 kilohertz. And just let me know if you can't read this or if my handwriting's too messy, etc. So before we look at voltages, we've got a frequency here. So what I always tend to do is just convert that into our radians per second, so our omega. So it's going to be our 2 pi f, which is 2 pi times 5k, which is 1 by 10 to the 4 pi rad per second. Now that we've got this, Z1 is equal to 4 plus j omega L. This is our impedance for an inductor, which is equal to 4 plus j times this 1 by 10 to the 4 pi times our L, which is our 0.286 millihenry. And this is equal to 4 plus j 8.98 ohms, which we can convert to our rectangular form. It becomes 90.8 angle 66 degrees. Just check my working there. Hopefully that's all right. So we need our impedances first to then get the voltages. So let's find I V1 is equal to I Z1, which is just our 5 angle 0 times 9.8 angle 66 degrees. So we're looking at 49 angle 66 degrees. Let's not forget our units. So here we're looking at volts. And for II, we'll first need our impedance 2. So Z2, I'll just write it over here if that's okay. 8 plus, well, we might say minus 1 minus j times 1 on omega c, which is 8. Minus 1j, 1 on 1 by 10 to the 4 pi times 1.273 micro. If you spot any mistakes, please just yell them out to me. So this is going to be 1 on 1 by 10 to the 4 times pi 1.273 10 to the minus 6. And feel free to also post in the chat if it's going too fast or too slowly. So we've got our Z2, so then V2 is equal to I times Z2, which is equal to 5 angle 0 degrees times, let's convert this to our polar form, so 8 minus 25I is 26 angle minus 72.3 degrees. If these sort of conversions are taking you a bit of time, I recommend trying to speed them up as much as you can, just because we're we're under time pressure. So being able to do this very quickly will save you some precious moments in your midterm. Angle minus 72.3 degrees, and that's in volts. Cool. Alrighty, so that's this first question. We've got the voltage. Now, power factor across the combined impedance. So if we're looking at the combined impedance, essentially what we're looking at is the voltage from here to here, V total. So V total is equal to V1 plus V2. So we might just transfer these into rectangular form just to make our life easier. So feel free to please follow along as well while these questions are being done. To like check with me, because everyone makes mistakes, but also for your own. So this is V1, and then V2, we're looking for this 131.2 angle minus 72.3. $40 minus 125. Plus 44.76I plus 40 minus 125I to 59.93 minus 80.24 J. So this is one way to do it, is to look at the voltage, and then once we've got to this, we turn it into our polar form, and then we can turn it into using power factor is equal to cos of theta v minus theta I. But another way to do it, to look at this, is to say, well, power factor is just the angle of Z total. So this is just going to be, sorry, I beg your pardon, cos of the angle of Z total. So this might save you a bit of time, because instead of having to work through these voltages and then multiply by a current, excuse me, you can actually just use the impedances that we've calculated. So this is just going to be cos of, the angle of Z total is going to be the angle of Z1 plus Z2, because they're in series. So J 8.98 plus 8 minus J 25. It's going to be cos of the angle of 12 plus, minus J (16), which is the angle of that 12 minus 16j is minus 53 degrees. So sorry, I'll just scroll down. So cos of minus 53 degrees, which is going to be .6. Now, is this leading or lagging? Any thoughts on whether it's leading or lagging? To fill in here. Remember, we always need to say whether it's a leading or lagging power factor. Leading. Yep. Excellent. So because we've got this negative here, that essentially means that our power triangle is pointing downwards. So this theta is negative, which means it's a capacitive, net capacitive load. So it's a leading power factor. Any questions there, or that's all good? Is anyone a bit worried about this different approach using the angle of Z total? It might be worth just having a look at if we'd done this using V and I instead. So hopefully they should be equivalent. So if we convert this V total into polar form, we get angle minus 53.24 degrees. And then if I is equal to 5 angle 0 degrees, then theta V minus theta I is equal to minus 53.24 degrees minus 0 degrees. And we get the same answer, right? So essentially, it doesn't matter as long as you're comfortable with whichever method, then you can start to find these tricks to save a bit of time. So that's our power factor. Oh, beg your pardon. That's our power. What's going on? Power factor of our combined impedance. Number 2. Okay. So for the circuit in figure 2, supposing the load shown dissipates an average power of 400 watts. So the first thing I always do, I might just draw a line underneath all of this. Doesn't seem to want to click. Ah, that'll do. So we've got an average power equal to 400 watts. And we've also been given a power factor, we'll call this 1B, equal to 0.766. Lagging. Now let's draw out our circuit here. Actually, we don't need to. We've already been given this diagram. So for question I, we're asked the input current I. Now we know that this average power, P average, is equal to sort of this real part here. Can we download it? Yeah, sure. I think it's okay for me to make this available for you. Let me just find it. I think I can upload it here. Sorry about that. No worries. Thanks for bringing that up, Sam. So we know that our complex power here, S, is equal to 1/2 V M. Oh, I beg your pardon. Sort of 1/2 complex V, complex I, conjugate. So we've got this 1/2 here because these are max value, not RMS. So if they're RMS, we have that this magnitude here is V RMS I RMS. Magnitude of S, this is our apparent power. So just by simple trigonometry, we've got that P average is equal to 1/2 Vm Im cos of theta. Now, do we know theta? Yep. Arc cos inverse of our power factor. Exactly right. Because this is just cos of theta. Easy. And when we spit this out, cos of theta gives us 40 degrees. Now, is it plus or minus? This is an easy way to get caught out. Is missing a sign here. Plus 40, exactly right. Because we've got a lagging, I beg your pardon, a lagging power factor, which means it's pointing upwards. So theta is positive 40 degrees. Cool. But for this first section, we're looking for I, right? Complex form of I. So really, let's solve for Im here. So I, in phasor form, has two parts. It's Im angle theta I. So if we rearrange for Im first, we get that Im is equal to 2p on Vm cos theta. Now remember, cos theta is just our power factor term. So actually we don't need theta for this example, for this first part at all, just to find the magnitude. So now for Vm, we're given that if you don't get given that that it's RMS, just assume Vm. So assume this is the maximum value. So we're going to use Vm equals 100. So the values we're subbing in are 2 times 400 watts on 100 volts times 0.766. And this should give us an answer of 10.44 amps. So we've got Im, we've got half of our value. Now, theta I. How would we go about finding theta I? Well, I guess we can, yeah, Yuval. I guess we can turn to what do we know?
Wait, I'm sorry, I'm a bit confused. So
Yep.
the Vm that we are given in the question, that's like the total voltage, right? That's not across only the impedance.
Well, that is the total voltage across our circuit, and I is the current through the entire circuit. So we can just use this voltage. Does that make sense?
So like so in the question it says for the circuit in figure 2, supposing the load. So by load, do they mean just the Z part or like the full part?
The full thing. So this is the load.
Yeah,
you're right.
Then it makes sense because if only Z was the load, then we'd have to calculate voltage just across the load, which is why I was confused, like how to approach it.
Exactly right. Yeah. So I think with these sorts of things, if you really have no idea what's like, if it seems like there's a mistake in the question, you're probably overcomplicating, if that makes sense. So try just taking a step back and saying, okay, they want me to find the input current I. I assume that that's, that's the current through here, and the load is going to be this. Yeah, it's a bit how you interpret it, but I think it's reasonable to call this the load as opposed to just Z, because 4 ohms is a load. but you're right, it's not particularly clear.
Right, okay.
Thanks,
And
Yuval.
then, sorry, what was your question again?
I was asking, how do we find theta I? So from the information that we've been given, any thoughts? It might look a bit crazy, but I might just point out this section here where we found theta.
Because theta is like theta v minus theta I, right? So 40 is equal to 30 minus theta I, and then theta I would be minus 10.
Exactly right. So then we do theta v minus theta. Theta v, again, we can just come back up here. So I'll just write out here, Vm equals 100 volts. Theta v is equal to 30 degrees. So if we do our 30 minus 40 degrees, we get negative 10 degrees, and voila, we have I equal to 10.44 angle minus 10 degrees in amps. Cool. Any questions there on the input current I?
Wait, sorry, I just had a question about the source again. Sorry, I had
Yep.
to go do something, but it says RMS there, but...
Oh, does it?
Oh, no, as in like you've labeled it RMS.
Oh, sorry. I said if not given RMS, assume it's VM. That's not very clearly written.
Oh, okay, yeah. Assume, yeah, like Vmax, but...
Yeah.
Yeah, because they released like answers for like the 2018 paper, and they also just kind of assumed that the source was RMS, but it wasn't stated anywhere. So I was kind of confused.
Okay, look, maybe it's better to assume it's RMS then, in which case you'd use a different value here. If they don't explicitly say it, they can't, they won't take marks off you for using either. Yeah, I think it's a bit hazy here.
Yeah.
Yeah, so or even better yet, just write we assume VM.
Yeah.
And then you've got, a full leg to stand on. You're like, well, I said I assumed that. There was nowhere written that it was RMS.
Yeah, sounds good. Thanks.
Cool. No worries. Alrighty. So that's that first part. Now we're going to sketch the power triangle, and we're looking for average power, reactive power, and apparent power, and any relevant angles. So we've already sort of done that here, right? So let's just formalize it a little bit. So we said that we've got theta equals positive 40 degrees. So let's start with that. 40 degrees is nearly 45 degrees. This is part II. And obviously try and keep your working more linear than I have here. I'm just sort of going anywhere that there's space. So first of all, P equals 400 watts. We get given that. This theta equals 40 degrees. We've just worked that out. What else are we looking for? We're looking for our Q, which is our reactive power. Sorry, that's a theta. Q, and also the magnitude of S, our apparent power. So first of all, for Q, maybe let's do P tan of theta, because tan theta is this over this. Then we just multiply by P and we get P tan theta, which is equal to 400 tan 40 degrees. And check my working out here, but I think we're looking at 335.6 volt amperes reactive. So this is our units for reactive power. And apparent power is just Vm IM on 2, because we've assumed that these are max values. If you'd assumed they were RMS, it would just be VRMS RMS. And I've got that as 522 volt amperes. And that's really all we need. Units are very important here, so make sure that you write your units. Watts, volt amps, volt amperes reactive. But yeah, any questions on that diagram? Sounds good. And now we look to find the value of the impedance Z. So essentially, we've got a lagging power factor. So from that, we assume, well, it's probably an inductor, right? But let's prove it and let's find the value of that inductor. So first of all, we know that the angle of theta v, oh, I beg your pardon. Our theta equals theta v minus theta I, which is equal to 40 degrees. But this is also the angle of our impedance, because this is the angle of v as a phasor divided by I. So the nice thing about this power triangle is that it actually derives directly from something called the impedance triangle. So the power triangle is just a scaled up version of the impedance triangle. And it looks like this. R, X, and this would be voltage, I think. No, possibly not. If we multiply these by I squared, sorry, V on I think. Ah, Z, thank you. Yeah, that's it. Going mad. Z, cool. So if we multiply all of these by I squared, we get to our power triangle. But they have identical, because they're just scaled up, they're what's called similar triangles. And so we've got this same angle, theta equals 40 degrees here. And we already know R, which means we can find this X. So this is the angle of 4 plus, they call it Z. And to find the magnitude of this value, essentially we can do magnitude of Z times I squared is equal to our magnitude of S. So there we go, magnitude of Z, there we go. So it's a bit confusing calling this Z. So let's call this ZL. So Z is our overall impedance, and ZL is just for the inductor that we're looking to find. So then the modulus of Z is equal to the mod of S divided by Im squared. And let's find these values. So this is 522 divided by 10.44 squared. Which is 4.789. Please correct me if I'm wrong here. So then we've got that 4 plus ZL. Z is equal to this, which is equal to 4.789 angle 40 degrees. Then this is equal to 3.669 plus J3 ohms. This is accounting for, like, we've got sort of rounding errors through here. But essentially, what we can say is we can equate these. So ZL is equal to 669 minus 3. minus 0.33 plus J3 ohms. So if anyone's spotted any mistakes in here, just let me know. But essentially, this is one method to do it. So it's not the method, it's just one method. Cool.
Could we have done like VM equal to total impedance into IM?
Exactly right. So let's try it another way. VM equals Z total into IM. Oh, beg your pardon. Like this.
Yeah.
I think we want to be careful, like maybe the magnitudes here.
But it's VM, right?
Sorry?
Like, you might be right, because I was trying to do it this way and I'm getting like a different answer.
I see. Yeah, possibly that may be correct. I'm not quite convinced about my method here. I might erase this one. So let's say the magnitude is just VM on IM. 100 on 10.44. Yeah, 9.57. Yeah, that looks better. So then our angle is this. So 9.57 angle 40 degrees is equal to 4 plus ZL. ZL is equal to, is that the same answer you got? Is 9.57?
Yeah, like
yeah.
That's the answer I got, but I'm not sure if that's correct.
Yeah, I think, no, that's all good. I think I had an issue here with this converting to the impedance triangle, to the power triangle. So you've just got to be so careful with these calculations. 7.33 plus.
Actually, I think Leon posted like a very cool way to check it. Like we can just sort of simulate the circuit on LT-Spice quickly.
Yeah, definitely. Let's do that. Obviously, might not be able to do that in the exam. But good for now. Apologise if my answers were incorrect there. But this is essentially the first question. So looking back, it's just two sort of a bit to do with impedances and calculating voltages, and then a little bit of power factor, which looks like a lot of working, but has actually turned into quite nice questions. So is anybody LT-Spice? Anybody got any queries about that, or all good to move on? Cool. Alrighty. So now it starts to get interesting. So we've done a little bit of circuits. Now let's look at some signals. So I might just try and grab all of this and move it around. Cool. Okay. So, question 2. Oh, apologies. Question 2, we're shown a periodic function, f of t. So as soon as you see the word periodic, we think, Fourier transform. Cool. We get given some interesting integrals, which may come in handy later on, which we will come to see. But essentially, the question's asking us to determine the trigonometric Fourier series of f of t up to the harmonic fundamental frequency only. So n equals 1. So we essentially what it's asking us to do is to write it out as an infinite sum, but sort of stopping at n equals 1. So to begin with, we're going to need f of t. We're going to need our period, and we're going to need our omega naught. So does anyone know what f of t is?
X minus 2, I think. T minus 2, sorry.
Cool. Yeah, so if we have a look at this graph, it might not be immediately obvious, but essentially if you were to start down here, you can just do like y2 minus y1 over x2 minus x1 equals y minus y1 on x minus x1. So not sure if I've got that correct.
Should it be x minus 2?
X minus 2, thank you, thank you. So then we have y is our f of t is equal to t minus 2. So f of t is equal to t minus 2. How about the period? Essentially, it repeats every t equals 2. So our period is 2. Omega naught is 2 pi on t, which is pi. We sort of cancel our 2's. So first of all, let's come back up to these equations that we got given at the start. So the equation for A naught we don't actually have, but it's sort of intuitive, right? It seems like it's oscillating around here, so we should get out -1. So let's first of all do our equation for A naught, which is that A naught is 1 on t, integral from 0 to t of f of t dt. So it's a half integral from 0 to 2 t minus 2 dt, which we've done plenty of times. Just hoping this comes out. 2 minus 4 minus 0. So this is 2 minus 4 is our minus 2 minus 1. Boom! That's exactly what we wanted to show. So we can see that it's sort of centered around this minus 1. Cool. Alrighty. Now let's get into the fun stuff. So we're going to grab our equation for AN, which is here. Oh, that's not much help to me. Okay. So I'm just going to write that down. But I think I would recommend printing out a formula sheet with these on them just so you can quickly grab them if you need, or just memorize them. We're going to integrate from 0 to t. It's the same as minus t to positive t. F of t is our t minus 2. And then we're also multiplying by cos of n omega naught t dt. So let's break this out into two integrals. So this is 2 on 2, it just becomes 1. So let's ignore that. So it's integral from 0 to 2 of t cos n pi t dt, because remember our omega naught equals pi, and this is minus 2 integral from 0 to 2 cos n omega naught t dt. Here, this t cos of n pi t, we actually get told how to integrate at the start here. It's x cos ax. So let's use that one here. So 1 on n pi squared cos of n pi t plus t on n pi sine of n pi t. And then that's from 0 to 2, and then minus 2 minus 1 on n pi. Sorry, I should have written pi there. Sine of n pi t. If you notice any mistakes, please let me know. From 0 to 2. Continuing on, 1 on n squared pi squared cos of actually, I'm very sorry. I think we want to work in the region minus 2 to 0. Actually, it doesn't matter. 0 to 2 works fine. Let's do that. Cos of 2 pi t plus 2 on n pi sine of 2 pi t minus 1 on n pi squared cos 0 plus 0 times 0. And then this is minus plus 2 on n pi sine of 2 n pi. Sorry. These are all n's. Minus sine of 0. So all of our sines are going to go to 0. Sine of 2 pi n also going to go to 0. Cos of 2 pi n, remember any value of 2 pi, it's going to go to 1. Cos of 0 goes to 1. And all we get is that an, this is 1 on n pi squared, this is 0, this is minus 1 on n pi squared, this is also 0, so it just goes to 0, which is what we expect, because this is an this is, I don't think it's an odd function, but anyway, it's got this sort of look about it. It's got a sine. I don't actually know. Looks like a sine or a cosine. I think sines, which is why the cosine part goes to 0, which is our aim. Okay, so let's come back up to the top here. So we don't have any cosine elements, but let's have a look at our sine elements. So we know that there's going to be sine elements. So if we come back down, let's integrate for Bn. Again, this is all fairly routine. Feel free to let me know if you spot any mistakes, but we're doing 2 on t, exactly the same setup. F of t, except this time we're integrating with sine of n omega naught t dt. So 2 on 2 just goes to 1. Integral from 0 to 2 of t sine of n pi t dt minus 2. Integral from 0 to 2 of sine n pi t dt. So this one, we can again use our expression that we get given in the question. I'm just going to go through here to save a bit of time. N pi t minus t on n pi cosine of n pi t. 2 minus 2, 1 on n pi cosine of n pi t. Cool. This is 1 on n pi squared sine of 2n pi. So we already know that's going 2 on n pi cos of 2n pi minus sine of 0 is 0, and this t is going to send it to 0. So that goes to 0, and then we minus our 2. This is going to be 1 on n pi cos of 2n pi minus 1 on n pi cos of 0. So that's 0. So this goes to 1. This goes to 1. These cancel. So this whole term goes to 0. And let's come back here. So sine of 2n pi goes to 0. Cos of 2n pi goes to 1. This goes to minus 2 on n pi. Excellent. So coming back to the question, all we want to do is write out f of t to the first harmonic. So f of t is equal to a naught plus b1 sine of 1 omega naught t plus, and we don't really care. So a naught, we know it was minus 1. b1 is just going to be 2 on pi because n equals 1. It's bn. Oh. Minus 2 on pi. Sine of our omega naught was pi t plus on and on and on. And I write to the first harmonic just to show that you really know what's going on. Does that all make sense? Any questions with that one? Am I going too quickly or too slowly? How are people feeling?
Seems pretty good so far.
Okay, no worries. Thank you. So let's just move this stuff. Oh. It didn't work very well. Move it over. And let's get cracking on the next question. So that first question gave us a periodic function. Now we're given this weird looking non-periodic function. So we've got essentially a bunch of steps.
But sorry to interrupt you, but could you just like scroll up for 1 second? Yep,
absolutely. Where would you like me to go?
I just want to like see the answer. Like, what did you get for Bn again?
Negative 2 on n pi, I believe.
Negative 2 on n pi. Okay. Thank you.
No worries. Yeah, so that's the working there. Sorry about this sort of quick cancellation and stuff. But essentially, I always just keep the graphs in mind. So there's your cos and your sine. 2n pi is going to be anything that falls here or here, which is always 0. And for cos, it's always 1. If you have like pi, n pi for sine is always 0 as well. And it's minus 1 to the n for cos. Yeah. Anyway, I digress. So here we've got essentially f of t is a piecemeal function, which means that it's broken up like this. So you might have seen these sorts of things. It's -1 for t equals, for -1 less than or equal to t less than or equal to 1. It's -2, 1 less than or equal to t less than or equal to 2. And it's -1 again for 2 less than or equal to 3, t less than or equal to 3, 0 otherwise. So essentially, we've got these three components of f of t. So it makes sense that then if we look at the Fourier transform, so you can write the Fourier transform in a few ways. There's this fancy f notation, or you can do just ft. It's a bit grungier, but it, you know, we know what you mean, and it's probably a bit quicker than trying to do that. So the Fourier transform of f of t is equal to integral from -infinity to infinity of f of t e to the minus j omega t dt. Now, if we just sub in our values of f of t, these serve as the limits of our integral, this serves as the value. So this is just equal to sort of a sum, -1 to 1 of -1 e to the minus j omega t plus the integral. So we don't need these whole infinities, right? It's 0 pretty much everywhere else. Integral from 1 to 2 of -2 e to the minus j omega t dt. Sorry, I forgot dt. Plus the integral from 2 to 3 of -1 e to the minus j omega t dt. Continuing on, these are just, we just treat these as constants, right? Because it's in terms of dt, j doesn't really matter. So we can do -1 on j omega e to the minus j omega t, -1 to 1 plus, sorry, -2, -1 on j omega e minus j omega 2, 1 to 2, and you get the picture. So this one's actually, it's pretty not too bad question. Any questions on this integration, or it seems okay? Okay. If you've got any worries or anything, feel free to stick your hand up or anything like that. If not, let's keep going. So we can cancel our negatives here. You get 1 on j omega e to the minus j omega t. E to the minus j omega minus e to the j omega. And then we can go +2 on j omega e to the minus 2j omega minus e to minus j omega. I think the main thing here is just really try and keep track of your negatives. So it's very, very easy to lose a mark for I might just write these the other way around, for having negatives, losing negatives essentially. Minus 2j omega. And I think we can just sort of leave this as is more or less, but let's pull out a 1 on j omega e to the minus j omega minus e to the j omega. This we could turn into a sine of some form if we wanted to, plus here we have e to the minus 2j omega. We have 2 of them, but then we subtract 1. So I'm just going to add 1 of them. And for the e to the minus j omega. We have 1 here, 2 here, and then but just check. Minus 3. Oh, I beg your pardon there. Yeah, anyway, so this one gets subtracted with that one, which means we want a negative e to the j omega, e to the minus j omega. And then also the e to the minus 3j omega. And that's it. So actually, that wouldn't be a sign. That would look like some sort of cos. That's essentially all you need to do. And then you can just say that this is our f of omega. So you could plug in omega to this quite happily. And that's sort of a fine way to leave it. Does that sound good? Cool. Okay. Let's keep going. So we've done B. We've found the Fourier transform. Suppose the f of t is shifted left by 2 seconds. So essentially, instead of happening at -1, this is -3. It goes down, etc. I can draw it in a different color. And then it goes until -1, and then it drops down. And that should be 2 seconds ahead. Cool. So that's our new one. This is g of t. Find the Fourier transform of g of t. So I don't know about you, but I really don't want to do all this integration again. So let's get cheeky and instead use some properties of our Fourier transform. This is sort of an iconic question for making you use the properties. So I've got the g of t is equal to f of t plus 2. Now, we've got the property that f of t of well, this may not be so much properties, but we've got, let's take a Fourier transform of each side. So let's say the Fourier transform of g of t is equal to the Fourier transform of f of t plus 2. Now this is the same as, you can actually derive this. It might be worth doing just to have a look. This is the same as the integral from -infinity to infinity of f of t plus 2 e to the minus j omega t dt. And then if you use tau equals t plus 2, we can actually make this the integral from -infinity to infinity of f of tau e to the minus j omega tau minus 2 d tau, because this d tau is the same as dt, so we can just replace that. And this is equal to e to the j omega 2 integral from -infinity to infinity of f of tau e to the minus j omega tau d tau. And this right here is our f of omega that we've already derived. Because tau and t can be the same, like it doesn't really matter. They're just dummy variables. So let's use this property that shifting in time by 2, so f of t plus t naught, if you take the Fourier transform of that, this is equal to e to the j omega t naught Fourier transform of f of t. So we can essentially say that the Fourier transform of g of t is just equal to the Fourier f of omega times e to the j omega 2. 1 on j omega, and then just copy this across. But you can see that we've already got a bunch of e to the j omegas. So I'm just going to carry this through. So minus e to the j minus j plus 2j omega gives you j omega, and then e to the that minus e to the 3j omega. So this is just sort of adding all of the exponents. And then plus 1 because they cancel, and then plus e to the minus j omega. And that is our answer. Sweet. And we can just come back and stop here. So that's question 2 completed. Was there any questions at all about what we've done here, or any comments or things that you might want clarification on?
So if we get a question like this in the exam, would you recommend us to like sort of prove the time scaling property, or like just sort of move?
No, definitely not.
So we can just mention that you can do this using the time scaling property, right?
Mm-hmm.
Okay.
If you need to, just start from fundamentals like I did here. So just say, okay, this is what it's asking me to find. It's asking me to find this integral. And then, okay, the time scaling property meant that this happened, but this is a bit of a trick, you know? This is a trick.
Like one of the midterms, they asked to prove like the scaling property.
Yeah, and it's literally these lines, right?
Yeah.
Time scaling property. So that's exactly how you do it. You just have this change of variables, pull out the e to the j omega 2, and that's that.
Oh, this is actually the time shift property. Time scaling property is another one.
Oh, time shift, beg your pardon. Thank you. I forget the names. Essentially, if you can remember how they come out, you sort of don't have to worry about memorizing them. Like I didn't memorize this, but you've got a formula sheet anyway. So just knowing these things exist, knowing that you can time shift and still avoid a whole bunch of work is really useful. So just look out for that.
Right. Okay.
Cool. Anybody else have any thoughts or queries or questions? No worries. Alrighty. Well, let's have a look at question 3 then, because these are sort of more of the trickier questions that we might come across. So, first of all, we have this circuit, and we're looking to prove a transfer function. So this is the form that we want to get it into. Now we can see there's only these 3 components, and actually this is in the Tute lab, right? So we've seen this circuit before. It might look like a bit of a different equation, but you know, we're familiar with this. So I might just, oh my gosh, I've not been doing a very good job keeping this neat. Let's move this all. Cool. Has the drawing been okay? Can everyone sort of read and follow along all right? Do I need to zoom in at all or anything?
I can read it fine.
Okay, thanks so much. Cool. So first of all, we've got this circuit in the time domain. So let's transfer to frequency domain. So we've got our plus or minus VI, our R, 1 on J omega C, and J omega L, and this is plus or minus VO. Sorry, I'll make this a bit bolder. So first of all, let's be nice to ourselves and combine these two. So we'll call it maybe Z equivalent and say, well, Z equivalent is equal to 1 on J omega C parallel with J omega L. And this we've done this plenty of times. I can go through it, but it's essentially just that times that on that plus that. Which should simplify through if we multiply through, like get a common denominator. Sorry, this is 1 on J omega C. And this, after a few steps, becomes our J omega L on 1 minus omega squared LC. That's our Z equivalent. So now let's find our transfer function H of J omega. It's just V naught divided by VI. So it's a voltage gain. And essentially, we can just do a voltage divider on this, right? This circuit becomes sort of plus or minus V, I, R, Z equivalent. This is the voltage here. So it should come out pretty nicely. So let's do the voltage divider just without writing VO. So this is Z equivalent on R plus Z equivalent. Which is this thing divided by R plus this thing. This is nice having sort of a denominator because we can essentially just cancel that denominator once we've multiplied this R by it. So this will make your life much easier in simplifying. So let's imagine that we've sort of multiplied this one by 1 minus omega squared LC on 1 minus omega squared LC. And then we can cancel these ones. And we get J omega L on R 1 minus omega squared LC plus J omega L. And then to get to the next step, let's just divide by, what would we divide by? J, L. Let's times it by something instead. So multiply top and bottom by our 1 on JLRC. So this cancels, we get omega on RC on, essentially the reason I chose this is just from the question, right? So I have a look at this. Oh, sorry, it's way up here. And I see, okay, I've got an omega RC on numerator. So how do I get to an omega RC in my numerator? Well, I have to multiply top and bottom by that. And then if you follow this through, we get omega on RC, that's from this term here. And then we get minus J, because this J sort of comes up into here, multiplied by 1 on LC, so that's this 1 here, and then minus omega squared, because the LC and R all cancel. And so if we come back to our initial, looking for a magnitude response, beauty. So this is our final H of J omega. So then let's take the magnitude of H of J omega. And if you aren't familiar with taking magnitudes, it's pretty easy. So essentially anything that's real just gets converted. Anything that's got an imaginary part, just do the modulus of each of the parts squared. 1 on LC minus omega squared. And if we compare, I think I did them the wrong way around, but that's okay. It's exactly the same. That's H of omega. Done. 5 marks. Not too bad. Not too bad. So just be smart in your algebraic manipulation. So like this trick of cancelling these denominators has saved me a lot, because we get this nice expression. So always look for common denominators. And then essentially just knowing how they want. Yep, was someone.
Well, I don't understand how you went from, I'm sorry, like if I missed it, but like, how did you go from, you know, where you have like that green tick, like that yeah, like sort of, so I get that equation, like that, yeah. That's just simply sort of doing the impedance and then reducing it. Then how do you get to the next step?
Okay, so what I'm doing here is I'm timesing the top by 1 on J RLC. And I'm timesing the bottom by 1 on JRLC. Sorry about this.
I remember you were explaining this, but I'm so sorry I missed it.
No, that's
okay. Why are you multiplying it by this again?
So essentially, essentially what it's doing is I want this on the numerator, right? So I had a look at the question. And it wanted me to have this omega on RC. So I said, right, what do I have to do to get this numerator to be omega on RC? What I have to do is multiply it by 1 on JRLC. So this RC is what I want on the denominator, and I'm getting rid of these J and L. Does that sort of make sense?
Yeah, like now it makes sense.
Yeah, and then whatever you do to the top.
So like I've seen some papers in which like they just ask you to find the, let's say, the response instead of sort of, so the question is like find the response of this circuit. So we can just leave it at the above expression, right?
Definitely. So this is the way to go if, but sometimes it's quite nice to have this in terms of like a real part on the top, but it doesn't really matter. So I might divide this through by J, just to sort of get it a bit neater, but you wouldn't be expected to get it into, because how are you meant to know, you know?
Yeah, exactly. Okay.
Yeah, so no worries there. This was just sort of a nice question in that we got given the transfer function. But if you're not, don't stress about what it looks like. Cool. Okay. Anybody else wondering anything? Alrighty. Sounds like we're all good. So now we're asked to sketch the amplitude spectrum of the output voltage V0 versus omega. And we're also given that the input voltage waveform is it's a Fourier series. Sorry, I'm all over the place at the moment. So this VI is some sort of A0 plus the sum n equals 1 to infinity of etc., right? Sines and cos. So what we get is that actually we've got to look at this waveform, this voltage, break it up into a bunch of little cosines. And they're each going to be at a sort of sorry, I've lost my train of thought. They're each going to be situated at an integer multiple of this omega A. So let's start just sort of plugging in values. So this one is a fairly numerical heavy calculation. So let's get stuck in. So we're given in the question above that R is equal to 159.15 ohms, L equals 202.64 by 10 to the minus 6 Henry. I don't think we're actually given this. We may just have to work it out. Oh no, we're given it very specific. And C is equal to 5 by 10 to the minus 6 farads. Cool. So Vi of t is equal to 2 cos of 31416 t. So in its phasor form, Vi of omega is equal to 2 angles 0 degrees. Now, we know that the modulus of h of j omega is equal to mod V0 on Vi. Now, we know what this modulus is. We just worked it out. It's 2, just from like phases. And we know what this one is because it's just sitting up here. It's some expression in terms of omega. So let's put these two together to find an expression so we can break this up as mod V0 on mod Vi. So then mod of V0, which is what we're interested in, is the modulus of h of j omega multiplied by the modulus of V in. So this is the nice thing about the frequency domain. If this was in the time domain, we'd have something called a convolution. But here we just get to multiply our transfer function, which is essentially what the circuit does to the signal, by this input signal, which is our cos. So we've got this expression. We know Vi is 2, so it's 2 mod h of j omega. So that means that the modulus of V0, sorry if it's quite little, is equal to room 2 times that big nasty expression that we found before on that 1 on LC minus omega squared plus omega on RC squared. Cool, so we've got an expression for it. So this is the thing that we want to be graphing. Now, we've been told that the input comes as a Fourier series of cos of omega naught A. So what that means is that we can plug in each of our values, our integer multiples of omega A. So let's find the modulus of V naught equated when well, maybe let's start with when omega equals 0 or DC. So this is our expression here. I'll just move it up here. Q. So if we plug omega equals 0 into this, that goes to 0, that goes to 0. Essentially, the whole thing goes to 0. So it's 0 volts at DC. What about when we plug in omega equals omega A? This is essentially n equals 0, n equals 1. So this is equal to 2 times, it's a bit annoying, but 31416, it's just mostly numerical things. So making sure that you're being very precise with your calculator use. Is always important. So I'd recommend maybe storing this square root value in like A in your calculator and this one in B, and then you just do 2 times, actually do it the other way around. I know it seems a bit like a bit picky, but doing things like that, you know, you're just less likely to make mistakes. And then this is plus 31416 on 159.15 times 5 micro squared, etc., etc. So feel free to work that out if you want. I've already done it. It's about 2 volts. So that's when it's sort of at its maximum. Let's have a look at when n equals 2. So omega equals 2 omega A. Then mod of V naught evaluated when m omega equals 2 omega A. Exactly the same as this, 2, but then we've got 2 times 416. So might copy this. Oh, that didn't really work. That worked. So we do 2 times it, and then 2 times it here, and then 2 times it here, etc., etc., and we get 0.05 volts. I don't know how many of these it asks us to do. I don't think too many. And then if we sketch, essentially we're just going to have at omega equals 0, a 0 peak. At omega equals omega A, it's going to come up to 2 volts. And then at 2 omega A, so this is omega A, it's at 0.05 volts. And then at 3 omega A, it's at 0.03, and then 4 omega A, 0.02, etc., etc. And that's all we really need for this question. Any questions or queries there? Cool. Sounds like you guys are all good. So now we get asked, suppose that the frequency gets increased slightly and without performing any calculations. So they don't want you to do any spectrum stuff. Explain whether you expect the amplitude of the output voltage V0 to be larger or smaller. And then the hint here is consider the resonant property of the circuit in figure 5 if the voltage source and resistor are transformed to a current source and resistor. So essentially it's asking you to turn this into a parallel resonant circuit. So if we source transform, it becomes current source, resistor, capacitor, inductor. And we know from this that the frequency omega naught is 1 on root LC. And that means that actually this omega naught that they gave us here, if we calculate this, is actually the resonant frequency. So we're sitting here. So if we increase the resonant frequency, I mean, if we increase omega, so say this is omega naught. Essentially what we're doing is we're moving this way. This is omega nu. And does it make sense that sort of this magnitude here is way lower? Because this one here is sitting right at the resonant peak, whereas this one's sitting way down low. So we don't actually need to conduct any. What we would see would be that this peak would be much lower.
So I just calculated and it says like the resonant frequency is in fact 31416, what they gave to us in the question.
Yep.
So I believe like any frequency left to right of that, the magnitude would be less.
Exactly right. So essentially that's sitting at like the maximum value you can have. So if I zoom right in on this plot. So this value, oops, sorry. This value here, omega naught equals 31416. The output voltage is over the inductor. Yeah, good point, Leon. So let's have a look at that. It's across both, right? So it's across the inductor and the capacitor. Because remember, this voltage is across this node. So the voltage over the inductor might increase, but it'll be the same across the capacitor. So I think it's yeah.
No, I mean like after you convert it to like a parallel RLC circuit, then the voltage across every element would be the same. It's just that at resonant frequency, the impedance would be the minimum, which is why V output would be maximum.
Yeah, exactly right.
So even if you increase omega, like with that, the impedance will increase as well, which is why like the overall voltage will be less.
Yep. Cool. Alrighty. So I think we're all good there. Now we get to a fun little in magnetic, well, paired inductors. I forget what we call them.
I don't think we covered this actually.
Okay.
Yeah, so
that's all right.
So our lecturer, she hasn't gone over this.
That's all good. Let's move on. So essentially, you'll get to this later. It's just sort of KCL. It's pretty chill. I think you'll like this. Not for the midterm, perfect. Alrighty. Question 4. This should be okay. Fourier transform should be okay. I think the rest of this you would have covered. Yeah, thanks, Liam. Alrighty, no problems there. So that was it for question 3. Let's have a look at question 4. So before we move on from this one, was there any questions at all about this part? Or happy if we move on? All good, thanks, Sam. Cool. Alrighty, let's dive in. So question 4 is probably going to be the sort of challenging theoretical questions. I know it's all theoretical, but you know what I mean. These integrals and possibly derivations, etc. Let's have a look at question A. An integral from -infinity to infinity of e to the j10 omega delta of omega plus 1 d omega. Now, who can remember the special property of the delta function? Especially when it's under an integral.
Oh, that'll just evaluate the function in front of it at that particular value. So it'll just evaluate the exponential at -1.
Exactly right. Thanks very much, Yuva. And I think, yep, excellent. So we can see that we're trying to integrate e to the j10, which is, we don't really know what that looks like, but let's just pretend it's e to the 10. Oh, sorry. Bit big. So it's e to the 10, but then we have this delta that's 1. We've got an area under it of 1. We can't really say it, at -1. So that means that it essentially just picks out the value, the area under this at the point -1. Or the value of this at -1. This is just e to the -j10. Easy, 2 marks, right? So just remembering those little things can be really, really helpful. Now we're asked to derive the Fourier transform, f of omega. Did anyone have any questions about the delta function, sorry? I think that one's fairly okay. It's just sort of a property of the, you might be able to write that by properties of Dirac delta. Cool, if not, let's have a look at B. So we want to derive the Fourier transform. So it's very clearly derive for e to the -2t. So again, this is just going to be f of omega is the Fourier transform of. Now, note this too. For most of our exponentials, They start at 1, right? This 2 means that actually f of t is equal to 2 e to the minus t, 2t. So I know if it was quite a common mistake. I don't think they marked down for it, but you want to be the people who can spot this and say, actually, that's what that function is. So we're looking at 2 e to the minus 2t. Just little things like that. And again, let's just write out the expression. It's pretty standard by now. J omega t dt. These are going to combine, so we're going to have a 2. But we don't actually need to go from minus infinity, right? It's 0 beyond there. So let's just go from 0 to positive infinity. And this is e to the minus t 2 plus j omega dt. Integrate it, minus 1 on 2 plus j omega e to the minus t 2 plus j omega. Let's go to r and then take the limit as r goes to infinity. Just for correctness, doesn't really matter. Minus 2 on 2 plus j omega. Limit as r approaches infinity of e to the minus r times 2 plus j omega. Minus the limit as r goes to infinity of 1. Obviously, e to the minus r, as r gets really big, this is going to go to 0. This term goes to 0. There's no r here, so this is just 1. So this is just going to be 2 on 2 plus j omega. And thus, f of omega is 2 on 2 plus j omega. That's for this 2 e to the minus 2j. We could also do this just by properties. So we know that essentially we know what the Fourier transform of e to the minus t is. And so you can use time scaling to get that to 2t, and then you can also multiply it by 2. I'm pretty sure it's linear, so 2 f of t is the same as 2 f of omega. But you can have a play around with that if you want. That's another way to do it. There's A and there's B. Maybe not. Be a bit whack if you had to derive everything. Oh yeah, that's why it said derive. Thank you. Thanks, Leon. Yeah. So that's why they underlined the derive here, because otherwise, yeah, exactly right. 6 marks. If you can do the same thing in like 2 lines. But these properties are a good way to check. So if you like, don't know if that's right or not, check using these. Always worth it. You know, because that's 6 marks. Might make a bit of a difference. So moving on to this question, unless Leon or Sam, you guys have got questions, I'll just wait for a bit. Okay, it's all good. So here we get given that e to the j omega t has a Fourier transform of 2 pi delta omega minus omega naught. And then we get given this cosine and this sine. So I think the most important thing to remember here is cos theta is equal to e to the j theta plus e to the minus j theta on 2. And sine of theta is equal to e to the j theta minus e to the minus j theta on 2j. With these two equations, we can turn all of our e's into cosines and sines, and we can turn these cosines and sines, more importantly, into something we can then take the Fourier transform of. Yeah, sure thing, Sam. Is that this working here? Just highlight check by property. No worries.
Okay, thank you.
All good. So we're looking for the deriving f of omega with regards to this f of t. So let's just come over here. So we're given that f of t, f of t is equal to 3 cos of 50t minus 2 sine of 150t. So let's consider g of t is equal to 3 times e to the j 50t plus e to the minus j 50t onto minus 2 times e to the j 150t. You might see where this is going. That's good. Feel free to sort of jump ahead if you're following along. E to the minus j 150t on 2j. Now, g of t, this is actually equal to f of t, believe it or not. Exactly according to those rules that I wrote before. So I'll just copy those over here. Make sure that we've got them firmly in our head. Okay. You come over here. So hopefully everyone can see the resemblance between this e to the j theta. Here theta is 50. E to the minus j, 50t. And here it's 150t for the sine. So now let's take the Fourier transform of g of t, which is actually equal to our Fourier transform of f of t because they're the same function. And we can say this is 3 on 2 times 2 pi delta of omega minus 50. So the Fourier transform of this is 2 pi delta omega minus 50. This one is 2 pi delta omega plus 50. So I'm just going to go through 3 on 2 times 2 pi times that plus that. And then here we have minus 2 on 2j times 2 pi delta of omega minus 150 minus delta of omega, delta of omega plus 150. And then we can simplify through. These cancel. That cancels. Actually, we probably don't need to simplify any more than this. But it's nice to, just for your marker. But if you're feeling malicious, feel free not to. As long as it's readable. Actually going to be plus j2 pi and that, and then this is essentially our answer. And we could have done this just by taking the Fourier transform directly, right? Feel free to prove that. You know, we know by by sort of by properties that this would be 3 times pi delta omega minus 50 plus pi delta omega plus 50. But we're essentially taking the exponential root because they said given that this. But you could, yeah, this is all that we get given, so that's what we have to use. And now we want to sketch the amplitude and phase spectrum. So here we've got, this is our f of omega. So let's begin with the phase of f of omega. So I might just draw these two top and bottom. Sorry, not the phase, the magnitude. Let's start with our magnitude. Sorry, I'm trying to make these perfect, but they really don't need to be. Apologies. Okay. So first of all, the magnitude of f of omega. You can see that we've got these deltas. And deltas in the frequency domain are essentially just spikes, right? So we have spikes sitting at 50. So that would be plus here. And also negative 50, and then negative 150, and also, if I can fit them all in, 150. So the height of these 50 spikes are 3 pi, so we go zoom and zoom. And the 150 spikes are at 2 pi. So this is 2 pi. Zoom and zoom. So it's good that it's symmetrical. So we know that that's what happens for our cosines and sines. And then let's look at the phase of f of omega. So again, we're going to have these exact same values of omega. 50 and 150, this is omega. Now, what's the phase of this first one? Actually, this first two even. Does anyone have any idea what the phase might be?
So 150, it will be 90 degrees, and then at minus 150 degrees, it will be minus 90.
Awesome.
That's it.
Yep, that's perfect. Thank you so much. So here we have real vowels, right? These are real. For if we sub in an omega, right? So a delta is just going to give us a certain value. So essentially what we get is that, well, these have zero phase. Here we have a J. So a J automatically puts us somewhere on the plus or minus 90 axis. But a good spot is this minus sign. So minus is very important to our phase because essentially this is J times that, and this is minus J times that. And J lives up here, minus J lives up here. So this comes up, oh, that was terrible. Goodness. This comes up here, this one comes down here, and that's our phase. Excellent. Okay. Final question. Looks like we're just about out of time, but I'm happy to go through this one. Oh, we have a couple more by the looks of it. What if it was negative cos? Would we write plus or minus 180 degrees? It doesn't matter. either like they're the same essentially. You can go plus, maybe minus 180, I would think, just if you had to choose one. So we may just move on from question D if anyone has any worries there. Just let me know, or if not, let's have a look at this question E. So we want to prove from first principles that max average power transfer occurs when ZL is the conjugate of ZE. Essentially, let's say we have some current I through here. The average power is equal to I squared ZL. We can say this is V divided by ZE plus ZL squared times ZL. Now, what we want to do is actually take a derivative here. So we're looking for max. So if we see max, think derivatives. So dp, and maybe let's take it in terms of dz. This is equal to V squared times ZL squared on ZE plus ZL squared. This is equal to, by quotient rule, ZE plus ZL squared minus 2 ZE plus ZL all over ZE plus ZL to the fourth. Now let's set this equal to 0. So then we get that ZE plus ZL squared minus 2 ZE plus ZL. Sorry if these look like 2's as well, equals 0. And we can see that ZE plus ZL equals 2 ZE plus ZL. Sorry, that's squared. Now we can also convert these into, might be better to convert them into the real part and the imaginary part. So if we had like ZE squared plus 2 ZE ZL plus ZL squared is equal to 2 ZE plus 2 ZL. I think actually taking the derivative in terms of ZL was a bit misleading. We actually sort of want to break this up into Z plus R. So essentially what we see, let's imagine that the that these ZEs are purely like real, sorry. So I'll just get rid of that. So we get that oh, I beg your pardon, I missed a ZL up here. multiplied by ZL. So ZE squared plus 2ZE ZL plus ZL squared is equal to 2ZE ZL plus 2ZL squared. And these cancel. We get that ZE squared minus ZL squared is equal to 0. ZE plus ZL and ZE minus ZL equals 0. And what these tell us is that ZE is essentially has to be the complex conjugate. Oh, sorry, ZL has to be the complex conjugate of ZE. In order to satisfy this equation. And that's sort of all we need to show in order to make this question work. So you can see if these are real parts, it's just real squared minus real squared equals 0. So they have the same real part, but the imaginary part is where we obtain that. I think that looks right. Let me know if there's any issues there. We could also have taken this derivative in terms of like written these in terms of R plus R load plus X load, and then take derivatives and stuff. But yeah, essentially that's all we're looking for. Any questions here? I'm sorry we didn't get time to go through this question here. But that's no dramas.
Can we just quickly discuss that as well? So for part D, for first part, when omega is 0, then the capacitor would essentially be an open circuit. So like the voltage would be greater, right?
So if this is an open circuit, we just get a voltage divider.
Yeah.
V I of t. Yeah, which would be smaller. So it's asking will the amplitude of V naught be larger, smaller, or equal to the amplitude of VI? So if we have a voltage divider, that means the modulus of V
it'll be smaller.
Is, yeah, it's sort of like 1 on something.
Yeah.
It might be a half the modulus of VI, so it's smaller. Cool. And then
next part, the capacitor would be functioning, so we can like form an expression.
Exactly right. So you'd use your transfer function. Transfer function, have a look at it, and then consider whether this increase or decrease V naught's magnitude compared to V.
Okay, perfect.
Yeah, and the factor would be when you evaluate that at 2 pi on t. Cool. Alrighty. If anyone has any other questions, feel free to let me know now. If not, thanks so much for coming. And hopefully we'll send out the recording soon. So it's gone a little bit over time.
Thanks a lot.
No worries. Best of luck in the midterm, everyone.
Thanks for this.
That's a pleasure. Thanks, everyone. Thank you. Stop recording.